Hello guys, in this video we will continue developing our weather system. This part will be more intensive than the previous one, so don't be afraid. And let's start. As you know, the weather is very changeable. It has many states, but in most cases it's just the combination of the following two states: cloudy and sunny. Such things as rain, fog, snow can be used in each state independently. So what we're gonna do is we're gonna create two reference visual look styles for each state and combine them within our day and night cycle. To start with, we need to create a curve which will define at which particular hour one state of weather dominates over the other. So let's go back to our content browser, go inside our curves folder of weather system directory and create a curve. Right click, search for miscellaneous, then look for curve. Select curve float and rename it to C underscore weather type. Now let's open our weather type curve and add some points. The x-axis of the graph represents time. The bounds will be from 0 to 24. The y-axis represents weather type. The bounds will be from 0 to 1, where 0 is for sunny weather and 1 for cloudy weather. Now I'll make a curve and after that I'll comment on it. Now, the look of this curve means that from 9 o'clock in the morning till 17 o'clock in the evening, our weather will be cloudy, and the rest of the day, also our night, the weather will be sunny. Now let's talk about lighting. Our scene has two sources that have the most impact on it. It's directional light and skylight. We need to have a mechanism to adjust the intensity of these sources during day and night, also during sunny and cloudy states. For this, and for the sake of the purity of our project, we won't create multiple flowed curves. Instead, we will go with vector curve, but not the all dimensions will be used, only x and y. X-axis will be for our sunny and y-axis for our cloudy state. To do this, head back to our content browser. In Curves folder, right-click, select Miscellaneous, look for curve, select curve vector. The first one is for our directional light. Rename it to C_sun intensity. The second is for our skylight intensity. Let's begin with the customization of our sun intensity curve. I'd like to notice that when our sun goes down the horizon, it doesn't matter how much light it emits, because it doesn't have any influence on our surface. So the setup for our sun intensity will be very simple. For cloudy and sunny states, we will set specific value and it won't change during the whole period of day and night cycle. As I said earlier, we won't use all three dimensions of our vector curve. We'll go with x and y axis, where x is for our sunny state and y for our cloudy state. To work with specific dimension, we need to switch off the unnecessary one, like this. Now we need to define our time period, so we need to add 2 points. The first one is for our 0 hour, the second one is for our 24 hour. Press F key to zoom out. Now for our sunny state, we need to set the proper value. 4 or 5 will be enough, but actually it depends on how much bright scene you want to have, so it's up to you to decide. Next, let's move to our y-axis and do the same, but set lower value. If we have for our sunny state something like 4 in light intensity, so for our cloudy state, let's go with something 1.5. I think it will be enough. Now let's customize our skylight intensity. Because at night we don't have much light, our scene will be dark. So we will do a little trick. We will set our intensity at night higher than in our daytime, so we can see more details at night and our scene will be more attractive. It's not so realistic as in the real life, but for sake of our game, we'll do this. Well, the workflow is the same as it was in sun intensity curve. Firstly, I'll create curve, then I'll adjust it, and only then I'll explain my setup. So let's begin. So what do we see here? We have defined few periods of day: night, sunrise, daytime, sunset, evening. For night and evening periods, we set higher value of skylight intensity than for daytime. Next, we should do the same, but for our cloudy state. As you can remember, our x-axis is for our sunny state and y-axis is for our cloudy state. So, let's move to our cloudy state. So, our cloudy state is pretty much similar to our sunny state, but actually they are different. We can switch on the x-axis and see. Sunny state has higher skylight intensity at daytime than cloudy state. So, the basic customization of skylight intensity is done and we can continue. Now, let's go back to weather system and create references for sun intensity curve and skylight intensity curve. The first one, sun intensity curve. Change variable type to curve vector. The same for skylight intensity curve. Click compile and provide our curves as references. Compile and save. Well, I forgot to provide one more curve for our weather system to work correctly. Let's create another variable and rename it to weather type curve. Change variable type to curve float. Then click on compile and provide the curve to be the reference. Next, compile and save. Next, we need to create a function that will store all our weather system logic. The first elements to check are sun intensity and skylight intensity. We will see how they actually impact on our scene during day and night cycle. On the left side of your blueprint, look for Functions category. Click on cross and rename our function to Update Weather. Next, we need to drag and drop the following elements: weather type curve, sun intensity curve, skylight intensity curve, and current time. Now, pull a wire from weather type curve and search for get float value. Connect current time and promote return value to local variable. Name it to weather type. So anytime I need to know weather type, I don't have to copy paste this stack of nodes. Next, pull a wire from sun intensity curve and search for get vector value. Copy paste current size. Then right click on the return value of get vector value node and select split struct pin. As you remember, the x-axis is for sunny state and y-axis is for cloudy state. Now right click and search for lurp. Lurp, or linear interpolation, means the transition between two elements. Connect x to A input and y to B input. Next, drag and drop weather type and connect it to alpha. Do the same for skylight intensity curve. Now let's drag and drop sun and skylight references to our graph. And let's begin with sun. Pull a wire and search for set intensity. Connect the proper node and do the same for the skylight. Now let's check how it works in our game. For this, go to the construction script, drag and drop update weather function to our graph and connect it. Do the same for the event graph. Now compile. Next, go back to our level, select weather system and set day length to something small. For example, 0.5. It means 30 seconds. And let's check how it works. Bright night. Let's wait for our sunrise. And actually, not bad result for our daytime. Let's continue. Now, let's start developing weather components such as fog. For this, first of all, go to the project settings. Next, search for rendering category. Scroll down to the bottom and in shader permutation reduction category, check support sky atmosphere affecting high fog. Next, you should restart your editor and wait for shaders to compile. Now, let's create a curve for the fog, so we can define at which particular hour we need it, whether we need it during the whole day or just in the morning. For this, head back to the content browser and in weather system directory, go inside curves folder. Right click, select miscellaneous, next look for curve. Then select curve float and rename it to C_fog. Maybe timeline. As we are already in the curves folder, let's don't waste time and create two more curves. The first one for the rain and the second one for the snow system. Both of them should be curve float. Now, let's customize weather components timelines, and we will begin with the fog timeline. First of all, we need to define the bounds for our x-axis. They are 0 and 24 hours, as the length of our day and night cycle. Now, y-axis will be for the strength of our fog. Head back to the level and on your right in World Outliner look for exponential high fog. Here you can find an attribute called fog density. With such low value, we can actually see that the fog has no result on our scene. No impact, my bad. And the maximum default value for this attribute is 0.05. So keep it in mind when adjusting the values on our curve. Now let's head back to fog timeline and create some points to define at which particular hour we need our fog. For this example, I'll go with the following setup. Now, what can we see here? For the period from 5 to 8 o'clock in the morning, we will have fog, and for the rest of the day, there actually be no impact of our fog on our scene. Now, let's quickly customize rain and snow timelines. They actually be similar, and the reason is so I'd like to show you the potential of weather system we are creating. It will be in the end of the video, so just be patient. Open rain timeline and let's adjust our curve. You know the workflow. First of all, define time bounds. Next, add extra points. Then adjust their x-axis values. Now, let's talk about y-axis. In rain and snow timelines, y-axis represents a switcher. Basically, when we have 0, it means we have no effect of our component. And when we have 1, we have the full impact. So, adjust y-axis value. And from the look of this curve, we can say that from 14 till 18 o'clock we will have rain, and for the rest of the day we will have no rain. Do the same for snow timeline. And we are done here. Now we need to create particle systems for each of our weather components, for rain and snow. So for this, go up to the content directory, so we will be on the same level with blueprints and maps, and create a folder. As we're gonna use Niagara particle system in our project, I'll go with the name of Niagara for my folder, but you can rename it as you like. For example, VFX. Next, go inside our newly created folder and create another folder. Rename it to Weather System. So we will know for which feature our particle systems are referencing to. Next, go inside Weather System folder, and here we need to create our particle systems. For Niagara particle system, we basically need just two components, Niagara emitter and Niagara system. Let's create templates and then customize them. Right-click, look for FX category. Next, look for Niagara emitter. Leave the first element selected, new emitter from a template. So we basically have more components we need, and we won't create them from scratch. Next, choose Fontaine template and click on Finish. Rename it to NE, which goes for Niagara emitter underscore rain. We can duplicate our emitter and rename it to Niagara emitter of snow. Right-click, select duplicate, and rename it. Now, let's create our Niagara system. So basically, select each of Niagara emitter, then right-click and choose Create Niagara System. Rename it to NS for Niagara System underscore rain, and the same for snow. Save them all. Now, as we have our templates created, we can customize them. Let's start with the Niagara emitter of rain. Open it, and on the graph you can see a node full of attributes and stages. The execution of emitter goes in a specific order, from top to bottom, so make sure to put the necessary function or attribute in the right location. Now let's make our particle to look like actual rain. But first you need to decide on which side it will be computed, CPU or GPU. For particle systems that emits big amount of small particles, the best way is to choose GPU side. For this, go to emitter properties and in sim target change CPU sim to GPU compute sim. Now we can see a warning The emitter is GPU, but the fixed bounds checkbox is not set. For GPU particle system, we need to define bounding boxes, so our particle system won't pop up suddenly in case we are looking aside from our particle system. Don't get too high for these values. Make sure to set proper values. For rain, we'll go with minus 1000 on mean attribute to 1000 on all dimensions for max attribute. To fake the size of our rain, we need to do a little trick. Basically, particle system of rain will be attached to player character, so when our character moves forward, the particle system do the same. And to update in a proper way, make sure to check local space attribute, so particles will inherit emitter's origin instead of global space. As we control the life cycle of rain and snow components with the help of curves, we can leave emitter state block in a default state. Loop behavior set as infinite is okay for our particle system. Now let's move to spawn rate. Well, it's up to you to decide which value to use for spawn rate field. Our rain system will be very simple. I don't see any reason to make it complex. The actual result will be quite realistic. So, as for me, I'll go with the value of 10,000 and let's move to another block of our emitter. It's initialize particle. Here we can see a bunch of attributes, but actually we don't need all of them. So, for example, we can switch off mass, and we can also switch off sprite rotation. So we will have full control of our raindrops. As for lifetime, the values are good, so we can skip this attribute. And now let's talk about color. Raindrops aren't opaque and are not purely white, so we should make them look more dirtier and more transparent. For this, click on the white square and let's move to the value field. When we change the value field, it will have impact on red, green and blue channel at a time. Let's go with something like 0.6. Now you can see the difference, and all the channels have the same value. To make our raindrops more transparent, let's change alpha channel to something small. I'll go with the value of 0.02. Now press OK. And in the preview window, we can see that now our particles look more realistic and attractive. And we have only one attribute left, we need to check sprite size attribute and change the values. We need to have the shape of raindrop, so we need to lower x-axis value to something like 1, and in the preview window we can see that the result is quite good. We can adjust it later. We all have different tastes, so right now it's not important. So let's move on. Next we have location block. In our case it's sphere location, and it really doesn't matter if we go with sphere shape or change it to cylinder. So it's up to you to decide, but I'll leave it as it is, and I will only adjust sphere radius to something like 800. Now we have actually 3 blocks that have impact on our rain dynamic, in other words, on our velocity. Add velocity in column, gravity force, and drag. I don't really see any reason to go with complex logic for simple rain system. We don't need it to be physically correct. It's really the matter of taste. So I'll delete these blocks and add simple one, which is called add velocity. And I'll add it in our particle spawn stage. Now let's adjust the values. For very common rain system, we actually need to adjust on the z-axis, and we'll go with negative value, so our rain direction will be from top to bottom. We can go with something like minus 900. We can adjust it more precisely later when we actually add our particle system to scene and see how it works. But for now, let's move to another blocks. Now let's see what do we have in the particle update stage. We have 3 blocks. Particle state, it actually a manager for particle life cycle. It has only one Boolean attribute, which is called kill particles when lifetime has elapsed. So if you look in initialize particle block and take a look at lifetime attribute, you can see the bounds. So every time the particle goes outside the bounds, it is killed. So for this block, you don't need to change anything. And let's move to scale color block, as we want our rain to be consistent for the whole period of its lifetime. We actually don't need to change the color of our raindrops, so we can delete this block, and we have solve forces and velocity. This block computes all dynamic attributes and results of physics impact on our particles. For example, we have velocity, drag forces, gravity forces, maybe some custom forces. It computes them all, and in the result we have a normalized value. So we can skip this. Our particle actually don't fire any event, and we have the render stage left and only one block, which is called sprite renderer. Here we can see the basic material. Let me admit that Niagara particle system is not the topic for this tutorial, so be patient. Right now we need to create simple rain component, so our weather system will be complete. So we'll leave default material. Actually, for most people, the result we'll see on our scene will be very decent, will be enough for most users. Here we need to adjust only one attribute, which is called facing mode. We need to change face camera to face camera position. So every time we look on our particles, the rotation of our particles won't change. So the behavior will be very realistic. Now we are done with customization of our emitter. Don't forget to click compile and apply. So the changes we make in our emitter will be distributed to a particle system on our scene. Now let's see the result of our work. So go back to our level, drag and drop Niagara system of rain to scene. I'll reset its location to world origin, and we can see that actually our particle system doesn't work. To fix it, open Niagara system of rain and click compile. So changes made in our emitter here will be applied for our Niagara system. Go back to our level, and if your particle system is selected, you can see how the particles are actually rendered. Let's adjust its z-axis location to something like 200, and let's play and see. Well, I like the result. For this stage, it's quite okay. Let's move on to our snow component. Now, let's customize the Niagara emitter of snow. The workflow will be pretty much similar to how it was in Niagara emitter of rain, but with little differences. First of all, let's go to emitter properties and change simulation target from CPU to GPU. And make sure to set proper values for our bounds. Also check local space attribute. Next, let's move to spawn rate. Here we need to provide the value lower than it was in Niagara emitter of rain. So instead of 10,000 particles, I'll go with 5,000 particles. Next, let's move to initialize particle block. Here, make sure to switch off mass and sprite rotation attributes. The lifetime values are good, so we can skip it. As for color, purely white for our snowflakes is a good choice, but actually let's change the alpha channel value to make them look more transparent. I'll go with the value of 0.35 and don't forget to change sprite size. Let's go with something smaller, for example 2 and 2. Next, let's move to location block. As I said earlier, it's up to you to decide which shape to use. I'm pretty good with sphere. I only change its radius to 800. Now we need to adjust our dynamic parameters. As I said earlier, we actually don't need physically correct behavior. Simple velocity with a little bit randomness will be enough. So we can delete add velocity in cone, gravity force, and drag. Now, in particle spawn stage, let's add simple velocity. As you can see, we have simple three-dimensional vector and it has no randomness in it. So let's change it. On the right side, near the z-axis value, click on arrow icon, search for uniform range vector. So right now we have our bounds. Let's start with z-axis values. For minimum, I'll go with -100. And for maximum, -250. Next, let's adjust x and y axis. We can actually put the same values both for minimum and maximum fields. Let's go with -50 to 50. And now, in the preview window, you can see we have pretty much decent snow behavior. Next, let's delete scale color block because we don't use it. And we have sprite renderer block left. It's under render stage. As you can see, we have simple default material, but in future we'll change it to more realistic one. As for facing mode, we can actually leave it to face camera, so anytime we'll look up or down, our particles will always face the direction we are looking at, so we can actually see its round shape. Now let's drag and drop Niagara system of snow into our level and see how it looks in our game. Don't forget to press compile and apply. Now, as you can see, it's already been rendered. I'll just reset its position to world origin and click play. As you can see, the result is pretty decent. I'm really happy with it. Next, we need to create logic for switching on and off our weather components in our weather system. Go back to weather system and let's add two components. Both of them are Niagara particle system. Rename the first one rain component and the second one snow component. Next, select rain component and on the right side of your blueprint look for Niagara category and let's set the proper Niagara system asset for our field. Do the same for snow component. Now let's make our components inherit our player character's position. So every time we go in any direction, they will follow us properly. For this, go to the event graph, then drag and drop our weather components. From the first one, let it be rain component, pull a wire and search for attach component to component. Do the same for snow components. Next, search for get player pawn. The return value of this node is a reference link to our player character. Pull a wire and search for get root component. Next, connect the pins. As for snapping rules, we can leave rotation and scale rules in the default state, but for location rule, let's change it to snap to target. Now, connect this logic to the event begin play flow, click compile, and let's check how it works in our game. The shortcut for quick game launch is Alt-P. As you can see, we have both components working. Now let's move. And as you can see, when we are moving, our components are following us. There is a little artifact. As you can see, our effect looks like it's a screen space effect, but for this moment it will be okay. When we will do the advanced weather system mechanics, we'll add some world position offset, so there won't be such artifacts. Now let's add curve timelines for weather components that we created earlier. The first one will be for fog, so rename it to fog timeline curve. Change variable type to curve float. And do the same for rain and snow components. Press and compile, and provide each variable with a proper reference. Now, let's talk a little bit. You can have multiple levels, and each level can have multiple scenarios. For example, level 1 should have long daytime and short night time, and level 2 opposite, short daytime and long night time. So you need two curves for this. Our weather system is very flexible, so if you have multiple curves for each specific scenario, make sure to check an attribute called instance editable. In each curve you want to be modified. Also, there is another way to do it. Just click on the eye icon. Now press compile and go back to our level. Select weather system in World Outliner and take a look in the details panel. As you can see, now we have all our curves visible and they actually can be modified. So, for example, let's take rain timeline curve. we can press on the drop-down menu field and select any curve we want. Just like this, you can create many variations for each type of curve and have multiple choices with different scenarios, and your game can be actually very flexible. Now, let's add some Boolean variables so we can decide which type of rainfall we need for our level. The first one will be for fog. Rename it to bFog. Next one, rain, bRain. And the last one, snow, bSnow. Press compile and save. By default, Boolean variables have the false state, and we are okay with this. Make sure that our Boolean variables can be actually modified. For this, click on the eye icon. Now press compile and save. Now let's go inside update weather function and make logic for switching on and off weather components. The first one will be the rain component, so we need to drag and drop it to our graph. We also need rain timeline curve, current time, and our Boolean. Now we need to create two branches for each condition. The first condition will check whether we need rain or not. The second one will check at which point on our rain timeline curve we need to switch on and switch off our component. So if you need to quickly add branch node to your graph, you can use a shortcut. It's B plus left mouse click. And one more time. Connect proper nodes. Next, pull a wire from rain timeline curve, search for get float value. Now, as you remember, our rain and snow timeline curves have bounds from 0 to 1, where 0 is no effect and 1 is full effect. These curves are a little bit tricky, so when we check the condition, we won't be searching for equal, but we will search for nearly equal. And we are almost done. Pull a wire from rain component and search for two events, activate and deactivate. connect proper pins. Let's have a look. Well, if our value equals 0, it means we need to deactivate our component. So in case we don't want to rearrange our logic here, we can actually change the B field value to 1. So when our value equals 1, it's true, so we will activate our component, and if it's not, we will deactivate our component. And we have one more condition left. It's whether we don't need our rain. So we can duplicate deactivating logic and connect it to our condition. Like this. Now we can actually duplicate this piece of logic for our snow component. So let's do it. Let's only change proper components. Well, now we can test how it works in our game. But before we try, we need to deactivate our components for the default state. So what I mean, if we look in the viewport, we can see that actually we have our components working. As default state, we don't need it, so select both our components, and on the right side of your blueprint, in detail panels, search for auto activate. And deselect it. Now press compile and save. Now let's go back to our level. Select weather system in world outliner. And as you can see, we have our conditions. Right now we have two of them working. It's rain and snow. Let's see the result of our work in our game. For quicker preview, let's set day length to a smaller value, for example 30 seconds, so go with 0.5. We have no effect enabled, so when we launch we have no weather components working. Let's see. nothing happens. Next, let's activate rain, for instance. And you can see it starts raining. Now we can actually switch both of them and see the result. We have both rain and snow. Everything works fine. Now let's create this kind of logic, but for the fog component. For this we need fog reference, current time, fog timeline curve, and fog boolean. From fog reference, pull a wire and search for set fog density. Next, pull a wire from fog timeline curve and search for get float value. Next, we need to add branch. It's B plus left mouse click. Now connect proper pins. And let's have a look. If we do need fog, we go with this condition where the value of density is taken from the curve. In case we don't need fog, we actually have to set its density to very low value, so our sky atmosphere components won't draw a black sharp line on our horizon. So copy paste this block of nodes and set value, for example 0.001. Don't forget to compile and save. Now let's talk. As it comes from the name of component, high exponential fog, it's height dependent, so changing its height leads to different results. The higher it is, the more density of fog we have. Also, it's very scene dependent, but in most cases we have very common behavior. We have a scene full of fog from sky till ground. Weather system will only change global fog density. All other settings of high exponential fog should be adjusted in your level. Now let's go back to our level and I'll demonstrate you the possibilities of high exponential fog. For better visualization, we need to add some cubes on our level. So drag and drop it from Place Actors panel to our scene. I'll make some adjustments. well. And I think it will be enough. Now select weather system, scroll down to our Boolean variable and select fog. As you can see, now our scene is covered with fog and the value comes from the curve. And if we take a closer look on our cubes, we have some artifacts. It's due to we have mesh distances activated, and these artifacts come from skylight component. To remove them, we need to switch off cast shadows from our skylights. Don't be afraid that our scene become more brighter. It's because changing values in skylight leads to recapturing the light of all the scene. Also, make sure to check capture emissive only, so when we will update our skylight, we'll only capture emissive materials, so the capture will be less expensive. Now let's go back to exponential high fog. As you can see, we have a bunch of parameters. I won't go through all of them, it's not necessary, because only some of them can lead to very decent results, and it's just a matter of taste how you would make your setup of high exponential fog. I'll just show you how to get the most common behavior, and from this point you can start experimenting and acquire the result you need. Let's start with high of our fog. Changing z-axis to higher values, for example 15,000, leads to one look where our scene is covered with fog from sky to ground, and setting this value, for example, to negative 15,000 leads to another look where we actually don't see any fog at all. It's with the basic values in all parameters. Play with this value due to needs of your level and to behavior of your fog timeline curve. As for me, I need the high density fog when sun rises, and till afternoon it should disappear. For instance, I'll go with the value of 4,000. Next, fog high fall off, an attribute which controls fog density due to changes to its height. Small values leads to visible transition between sky and ground, while high values makes the transition less visible. For instance, let's change it to 1.5. The transition is less visible and all our scene is covered with fog. Play with this value due to your needs. As for me, I'll go with the value of 0.5. Well guys, I thought for a while and became with the idea to create one more curve for fog high fall-off. So by controlling global fog density and fog high fall-off, we can acquire very dynamic and smooth fog behavior. All other attributes, in most cases, can be static, but those two should be dynamic and controlled with curves. Only one change you need to do for your scene is to set proper z-axis value for high of our fog. Let me demonstrate what I mean. Now let's take a look at my drawing. We have two scenarios, A and B. For each scenario, you can have an independent curve. One curve is represented with the white arrow, is for fog high fall-off, and another curve represents fog density. For instance, this violet is low density fog and this blue high density fog. This black line on our y-axis represents our timeline. So as you can see, by controlling fog high fall-off and fog density with the curves during the day and night cycle, we can achieve very different results. I hope you understand the idea. So let's go to curves folder under weather system folder and create a curve which will be curve float for our fog high fall-off. Rename it to C underscore fog high fall-off. But before we start customizing fog high fall-off curve, let's make some changes in our scene at different periods of time, so we can predict which values we need to set in our curve to have the reference look we are looking for. We actually need to have 3 reference scenes. The first one is the sunrise, when we do need fog. The second one is the afternoon, where we don't need fog. And the third one is nighttime, just to be sure that night looks as it pretended to be. Let's begin with the first one. Go to weather system and set current time to 7.5. Now we can see our sun. Go back to exponential high fog and adjust settings as you like. I'd like to admit that fog and scattering color I prefer to have gray color instead of blue one, so it's more natural and can be used in most cases. Next, very important attribute is volumetric fog. We need it in case we want to have an attractive God rays and to have them activated we actually need to change some attributes in directional light. The light shafts. Switch on light shaft occlusion and light shaft bloom. We need to adjust occlusion mask darkness and bloom max brightness, so there won't be any artifacts and scene would look more realistic. Then we can go back to exponential high fog and continue with customization. Changing scattering distribution changes the way the rays from sun are looking at. So if we have small value, they are spread equally, I forgot this word, in all directions. And if we have high values, it's spread only in the direction we are looking at. U distance is how much area our volumetric fog actually affects. You can go with different values. I'll go with maybe 30,000. So on the horizon there will be no sharp line. So I like the way it looks, and I'll go to fog timeline and adjust fog density. So from 5 till 8, the value I need is 0.01. Next, I need to define which values should I have for the daytime and for the nighttime. but we actually haven't customized for high fall-off curve. So let's do it and set proper value. Then, only then, we will continue with our two more reference looks. The workflow you know. Add bounds, add extra points, the timelines should be pretty similar. My bad. Now we can continue. Now let's see how our scene should look in the afternoon. Maybe near it. Well, I like the values. Let's add them. Our 5, our 8. We actually need to define hours when our night starts. So let's say they are (21) and maybe 4 o'clock in the morning. Oh, I can't have 4. Let it be 3. So, for this period, I'll go with this value. The same for high fall off. Yep. And the last one is our night time. Now let's create the reference look of our night time. But before we start, our fog high fall off curve doesn't have any impact on the scene because we don't have an update logic in weather system. So let's create it. First of all, let's add a variable which will store the reference of our curve. Rename it to fog high fall off curve. Change its type to curve float. Then make sure to check its visibility so we can modify it. Then press compile and provide the proper curve reference. Now drag and drop our curve to the graph, also current time, fog reference, and let's begin. Pull away from fog reference and search for set fog high fall off. Next, from fog high fall off curve, pull a wire and search for get float value. Connect proper pins. Now, in false condition, where we don't need any fog, we also should provide default value. So copy paste this block of nodes and set the value to 0.2. Press compile and save. Now let's return to our nighttime look. Go back to our level. Select weather system and set current time to 3 o'clock in the morning. As you can see, we have no exponential high fog at all. That's because on our fog timeline, for this period, the value is 0. And if you try to launch again, you'll see only black screen. That's the way sky atmosphere component works with exponential high fog. To see a thing, you actually need to have some exponential high fog. Not very decent, but it should be. So let's see what we can achieve. Well, we actually have some light shafts, so we will need to create a logic to turn them off at night time. Let's provide our curves with proper values. Then select skylight, because we don't have recapturing logic right now. We need to recapture our scene. You can see the difference. Now we can try it in our game. And as you can see, our scene actually works fine. We just need to do some more adjustments. So first of all, our fog timeline and fog high fall-off curves, we need to provide the end of day period with the same value as the start of a day, so there is be no hitch during the play session. Like this. Like this. Now let's create logic for turning on and off the light shafts. We need sun reference, then pull a wire and search for get component by class. In component class field, look for directional light component. Then pull a wire from return value of get component by class node and search for set enable light shaft bloom. Next, pull a wire and search for set enable light shafts occlusion. Copy, paste these blocks one more time, and we need a condition. We should know at which particular hour to activate or deactivate our light shafts. So get current time, and in most cases, if our time is higher than 6 o'clock in the morning and is less or equals, maybe just less, 18 o'clock in the evening, we do have light shafts. Otherwise, we don't need them. Now search for end boolean connect proper pins, add branch node, connect everything and provide proper values. Press compile. Now let's take a look how it works in our game. Night. We don't have any light shafts. Now we have them. The sunset. Our night, no light shafts. Sun rises. And we have light shafts. Let's continue. Well, finally, we are almost at the end of our tutorial. We have only one thing to customize. It's the behavior of our sky in cloudy state. I'd like to admit that right now I'm waiting for the release of version 4.26 to have the full access for the volumetric clouds. So we'll just adjust the color of our sky during cloudy state and the size of our sun. Now select weather system and set current time to 9 o'clock. Then select sky atmosphere and let's talk about atmosphere ray light and atmosphere mirror categories. Well, let's begin with ray light. Ray light scattering scale controls the density of the atmosphere because of the ray light scattering. At high values, it can change colors from blue to orange. For example, right now we have the blue sky, and if we set, for example, 0.5, we can see that the color of sky changed to orange. So this is useful for sunrises and sunsets. Next, Rayleigh scattering. It's just the color of the atmosphere because of the Rayleigh scattering. Basically we have blue sky, but for example for the fog weather we can go with something gray. I said fog, cloudy weather, I'm sorry. Well, it's gray sky now. And Rayleigh exponential distribution, the value that controls the position of Rayleigh scattering fall off. So basically we can have darker sky at lower values and at higher values we have brighter sky. And we have Mie scattering left. This type of scattering occurs in the lower portions of the atmosphere. Such factors as smoke and dust are the main causes of this type of scattering. So basically, right now we can skip it and go along with Rayleigh scattering. Well, what we actually need to change in atmosphere Rayleigh scattering is scattering color and exponential distribution. We don't need to change scattering scale because out of the box it works pretty much well, and I can demonstrate it. For instance, switch off exponential high fog, then change our time, for example at 6 o'clock in the morning. As you can see, our sky has a gradient from blue to red. Let's change our time one more time. Well, you see, the behavior is pretty much realistic, so we don't need to change it. Let's create the vector curve for ray light exponential distribution. We need vector curve because for the x-axis we will go with sunny state, and for y-axis we will go with cloudy state. Rename it to C underscore ray light distribution. Next, go to weather system blueprint. Here you need to add a variable for our ray light exponential distribution. Rename it to ray light distribution curve. Change variable type to vector curve. Next, press compile and provide proper reference. Everything looks fine. Don't forget to make our reference visible so we can modify it when we need. Then drag and drop ray light distribution curve reference, current time, sky atmosphere reference, and that's actually all we need. So let's continue. Pull a wire from sky atmosphere and search for set relay exponential distribution. Next, pull a wire from relay distribution curve reference and search for get vector value. Next, right-click on return value of get vector float node and select split struct pin. Then search for lurp float. Connect proper pins, and for alpha we need current time. I'm sorry, not current time, but weather type. So basically, when we need sunny state, we'll read the value of x axis of our curve. When we need cloudy state, So whether type will be the one, we will read the y value of our curve. Connect everything. And let's continue. Next, what we need to do is change relate scattering color due to weather type changes. We will go with simple lurpin between two linear colors. For sunny weather, we'll go with blue one, and for cloudy weather, we'll go with the gray one. For this, we need to create two more variables. Each variable will be linear color type. Let's rename the first one to sunny sky color. Make it visible. Change type to linear color. And do the same for cloudy sky color. Now let's define default colors for our sky. As for sunny sky color, I'll go with this values. It's up to you to decide which color you like. And for cloudy sky, I'll go with this setup. Next, we need to create lurpin logic for our colors. So drag and drop each to our graph. Then pull a wire from sunny and search for lerp linear color. Make sure to have a input set with sunny sky color, because if you remember, weather type measures from 0 to 1, where 0 is sunny and 1 is cloudy state. Next, drag and drop sky atmosphere reference, then pull a wire and search for set relay scattering. Connect all nodes and let's continue. Next, we need to customize relay distribution curve. You know the workflow. The first one is our sunny state, so select only x-axis and deselect two others. That add points to define time bounds. And for this example, I'll go with simple curve. It will be straight line. Behavior you like, you will do on your own. So for sunny state, let's go with the value of 6, and for cloudy state, we'll go with a value of maybe 1.5. Now we can visualize the basic setups, and let's go back to our level and see how it looks. So we have changes. Our sky is great. Scatter distribution is low, because on my timeline I have a cloudy state from 9 to 17 o'clock. The whole picture doesn't look much attractive, but you can change it by adjusting some values in some curves. It won't take much time, so let's do it. Well guys, I realized that we can create a quick workaround to get rid of the white scattering of our fog at night. I know that for most of you it's not an option to go along with it. So basically what we need to do, in our exponential high fog, we have fog in scattering color, and changing it to dark one actually dismiss the effect of inscattering. The reason why we have this kind of effect is because right now it's 5 o'clock. If we set our time at 23, you can actually see there is very little scattering. Setting for color to the full black will dismiss this effect. So what we're gonna do, let's head back to weather system and create two variables. The first one will be for day, for color, change variable type to linear color, make sure to make it visible, and the second one will be for night fog color. Press compile. Now let's customize them. Now drag and drop our newly created variables to the graph. Then you need fog reference. Then pull away from fog reference and search for set fog and scattering color. Next. Now pull away from night fog color, search for lurp. As for the alpha, in case we want to have control and smooth transition between these two colors, we need a curve. Go back to our content browser into curves folder and create another curve. It will be curve float, and I'll go with name of fog opacity. This name I choose because basically I will be lurping between only two colors. The very common fog color is blue, and in case I don't want any fog at all, the color will be nearly almost black. So fog opacity is a good name for this curve. Open it, add point and set our bounds. Add some extra points so we can begin customization. And you can set your own values. I'll go with my own just to see that it works as it intended to work. And 0 value on our x-axis means black fog, and the value of 1, on y-axis means our common fog color. Go back to weather system, create new variable, rename it to fog opacity curve, make it visible, change variable type to curve float, press compile, don't forget to provide proper reference, then drag and drop it to our graph, then pull a wire and search for get float value. Now we need current time variable and connect everything. Press compile and let's check how it works. Well guys, I've made some experiments and recustomize my curves so we can have a pleasant result. It's just an example, so it's up to you. You can extend this system. I hope you understand the basic idea behind it. And this is just base weather system, so you can start prototyping with it, and after some time I will extend it by myself and create an advanced weather system. I'll show you my setup so you can achieve the same result, and it will be a start point from. So I'll open all my curves. Let's start with weather type. Weather type is a curve which controls the weather states, sunny and cloudy. So from 11 o'clock till 13 o'clock we will have cloudy weather, and the rain timeline is similar to weather type, so we will have rain at this period. Fog, rain and snow components are independent, so you can have them all at once, and they are not weather type dependent. Next, sun intensity. If you don't get this quick, you can press stop and see actually what values I have. I think there is no need to explain everything. Just look and experiment. And I have already told you everything that we have in this tutorial. After sun intensity, let's go to skylight intensity. It's night time, it's daytime. The red one is for sunny state, the green one is for cloudy state. Then relay distribution, cloudy, sunny, snow timeline, zero means no snow, 1 snow, our day bounds. Next, fog timeline. So from 7 to 9 we have some dense fog. The rest of the day actually no fog. As for fog high fall off, for my example, just straight line, it's quite okay. And fog opacity. As you remember, this curve controls fog and scattering color. So basically when we have 0, it's black color and there is no influence fog and scattering color at night. This is just blue fog color. So next, as for directional light, I set shadow amount to 0.5. Update this value every frame is very costly. So just for this basic weather system, we'll go with some constant value. Next, exponential high fog. I just scatter distribution, and I also changed its high due to need of my level. As for sky atmosphere, high fog contribution I set to 0.5, and for our skylight, actually it's costly to change it every frame, so basically we can activate engine content press on View options of the content browser, select Show Engine Content. So when we are in Skylight, we can actually change source type of our light to specified cube map and set the default one. Basically, we can go with the ambient cube map. If we look at it closer, we can see that up here is how lighting will be added in our daytime, and this when our sun goes down the horizon. Basically, adjusting skylight intensity in cloudy state will be enough for this moment to fake the lightning. For future, we will create a mini system for blending cube maps. Keep it in mind. Also, there is no cloud because I'm waiting for volumetric clouds, and when version 4.26 will be released, I will include them in our weather system. Now let's press play and see how our game works. I'll record it with a shadow play, so the quality will be higher and the frame rate will be higher too. As you can see, right now we have night, and actually it is snowing. Then we are waiting for the sunrise. Our ground is a little bit bright, so we can see at night more details. Here comes the sunrise, some fog. Well, next there will be some cloudy state of weather with rain. Let's wait for it. And here it comes. Actually, I hope you like what we did here. So, please leave a comment, subscribe, and I'm done with talking. Thanks for watching.